I'm going to be talking about our work on higher order random walks. This is joint work with Abchila. Let's first start by talking about what higher order random walks are. The scenario that I care about is where I'm given a collection omega containing k-elemented subsets of some ground set U, and I want to be able to approximately sample from the uniform distribution over omega. So higher order random walk is just going to be the name of the random walk or the Markov chain I'm going to be using to do this approximate sampling. And I'm going to be starting from some set alpha 1 in omega. And for every t greater than 1, I'm going to be getting the set alpha t plus 1 from the set alpha t in the following way, where I first sample an element y from alpha t uniformly at random. I then remove y from alpha t. And then the next step, I sample alpha t plus 1 uniformly among all the sets in omega containing alpha t without y. And one thing you can notice is that the uniform distribution is the stationary distribution for this. That is, if alpha t is uniformly distributed, alpha t plus 1 is also going to be uniformly distributed. And it is because of this we expect that when we run this Markov chain for sufficiently many steps, we will get really, really close eventually to a set whose distribution is really close to being uniform. And the number of steps we need to do this to get a set whose distribution is really close to uniform is called the mixing time of this Markov chain. And we will be studying this. And we will be studying this by way of studying the eigenvalues of this Markov chain. Let me give a few examples of this higher order random walk model. One application would be the so-called spanning tree exchange walk, used to sample a uniformly or approximately uniformly random spanning tree of a graph G. And in every step, what I do is, I maintain a spanning tree. At every step, I remove an edge of the spanning tree that I sample uniformly at random. And then I pick an edge that is not contained in the spanning tree uniformly and random to contain what is left, to complete what is left to a spanning tree. Again, this is related to the matter expansion conjecture. Another example is the Markov chain that we can use to sample an independent set of fixed size. So I'm given a graph G and a parameter K, and recall that an independent set in G is just a subset of vertices that doesn't contain any edges. So I want to sample an independent set of size K, which is approximately uniformly random. Okay, so I'm going to be maintaining an independent set, and every step of this random walk, what I do is I sample a vertex V uniformly from the independent set that I'm currently maintaining. And then at the next step, I'm going to be adding a vertex U that I sample uniformly randomly among all the vertices that are not contained in the independent set and that are not adjacent to any vertex that is currently in the independent set. Okay. Let me just talk about why I care about eigenvalues. I told before that what I care about is actually the mixing time. And mixing time is, roughly speaking, how many steps I need to run this random walk to get a sample that is close to the stationary measure of the random walk. And the stationary measure in our case is going to be the uniformly random distribution. So it's just the number of steps I need to run the random walk to get a approximately uniform sample, or rather a sample that is sufficiently close to being uniform. It turns out you can bound the mixing time of a random walk by the eigenvalues. That is, it's a basic fact in linear algebra that if you have a random walk matrix, its largest singular value is going to be 1. And it turns out the second largest singular value is from 1, the smaller the mixing time is going to be. That is, spectral expansion, or the second singular value, controls the mixing time. So what we want to do to show fast mixing is showing that the second singular value is bounded away from 1. Okay, why do we care about this random walk model? We care about this random walk model because it captures many important random walks that are of interest in both combinatorics and MCMC areas. And also it turns out to be important for agreement tests and some applications in coding theory. So it turns out to be an interesting model of random walk to look at. We want to be arguing mixing. And in the literature, there are several ways of doing this. There is the method of multi-commodity flows, coupling, log-solo inequalities, and etc. And what we want to do in our work, or rather the main contribution of our work, is adding a new-ish item to this list that is local spectral expansion. And it's really a new-ish item in the sense that it was used before, but it was used in a very restrictive setting. And our work is making this much more applicable. Okay, what is local spectral expansion? So we have this higher order random walk, and this higher order random walk is on a huge state space. And that's kind of making, arguing about it a little unwieldy. So instead, what we want to do is we want to argue about a smaller collection of graphs. And we want to say that because random walks on all those smaller collection of graphs are mixing very fast, it must be that this higher order random walk is also going to be mixing very fast. So this is some sort of local to global phenomenon. So we want to be roughly saying that this local walks, they have rapid mixing. So I have local mixing, and that local mixing implies the global mixing of the higher order random walk. And this local spectral expansion is not an idea that we came up with. It was an idea that I think was first described by Kaufman and Mass. There's been many works on it since then. In fact, particularly relevant for our work is the work of Dickstein, Dinner, Filmus, and Harsha, and the work of Kaufman and Oppenheim. But our work is the strongest one of these results yet. And all these results that are mentioned here, they have some regime in which they don't make any non-trivial, they don't give any non-trivial bound on the second singular value. But our work is really mild in this regard, in the sense that so long as some basic connectivity criterion is met, we can always give a non-trivial bound on the second singular value. Okay. So I want to be describing now what these local graphs whose mixing I'm going to be arguing are, and to this end I need to introduce the definition of a simplicial complex. So a simplicial complex is just a downward closed collection of subsets, and I will only be dealing with pure simplicial complexes generated in the following way. We take a collection omega of some grounds consisting of d plus 1 elemented subsets of some ground set U, and I define X just as a downward closure of omega. That is, whenever there is some set beta in omega, I add all the subsets alpha of beta into the collection X. Elements of X, I'm going to be referring to them as faces, and the dimension of a face is just going to be its cardinality minus 1. And the dimension of a simplicial complex is just the largest dimension of any face in that simplicial complex. And I'm also going to be introducing notation xj to refer to all the faces of dimension j. So with this notation, xd is just going to be the collection omega that I started from, and x minus 1 is just going to be the empty set because minus 1 plus 1 is 0, and there's only one set of cardinality 0, and that is the empty set. Okay, when we think about it, a graph is just a graph with no isolated vertices is just a pure simplicial complex of dimension 1. And in general, I can think of a general pure simplicial complex as a d plus 1 uniform hypergraph, where x minus 1 is just the empty set, x0 is a set of vertices of my hypergraph, x1 is a set of edges of my hypergraph, x2 is a set of triangles of my hypergraph, and so on and so forth. Okay, so in this language of simplicial complexes, the higher order random walk, or rather the down-up walk, does the following. We first sample, we start from a d-dimensional face alpha, 1. And for every step t, what we do to get alpha t plus 1 from alpha t is the following. We sample some y from alpha t uniformly at random, and then we remove it from alpha t. And this brings us to a d minus 1 dimensional face. And then among all the d-dimensional faces that contain alpha t minus y, we pick one uniformly at random and declare it to be alpha t plus 1. So this is called the down-up walk because I start on the level xt, then I go back down to xt minus 1, and I go up to xt minus xt. So I'm going down and up. So because of this is called the down-up walk. And I'm going to be using local spectral expansion to analyze this random walk. Okay, what is this local spectral expansion? This is a method that utilizes the expansion of some local graphs. So let me describe what these local graphs are. And to this end, I'm going to say, okay, let's take alpha to be a j-dimensional face in a d-dimensional simplicial complex, where j is smaller than d minus 2. And let's look at the lattice of all the faces in X which contain alpha. So in the bottom of this lattice, we're going to have the face alpha. And in the very top of this lattice, we're going to have all the faces in XT that contain alpha. So the graph I care about is at the very bottom of this pyramid. And it contains faces of dimension j plus 1 and j plus 2, where j is the dimension of alpha. So I can think of this blue area like a graph by just saying, okay, like every j plus 1 elemented face that is contained in there is essentially corresponding to a vertex because it's of the form x union alpha. So I'm just going to say, okay, x is the vertex of the graph that I care about. And for every j plus 1 dimensional face in there, which is of the form xy union alpha, I can just say it's corresponding to an edge xy. And I can also give a weight to all these edges by essentially looking at the number of times they're contained in a top level face. Okay. So this G alpha is essentially the local view of the face alpha. And I'm going to be abusing the notation a little and write G alpha for the random walk matrix where the transitions are proportional to the weights W alpha. What was known before is this theorem of Kaufman and Oppenheim that assumed a bound on the second eigenvalue of these local matrices, and based on that bounded the second singular value. And this was a very useful result in the sense that this was how the metric expansion conjecture was resolved. And this was a long-standing open problem in the area of Markov chains. So, this is a very good result in that sense. But this is a result that is really hard to use because it is very aggressive in the demands it makes to, the bound on the expansion. It demands very aggressive expansion. And in many cases where one would be interested in applying this, this expansion requirement is not met. So in many cases, we really think of D as n, or order n. And these link graphs that we care about, they're graphs on n vertices. And we're demanding expansion 1 over n squared. This is really too aggressive. There aren't that many graphs that are interesting, that are on n vertices, and they're off. They have second eigenvalue bounded by 1 over n squared. This is too restrictive. So what Labche and I prove is this refinement, where we replace this additive form with a product form. And our bound also, instead of bounding every face uniformly, so instead of bounding the second eigenvalue of every face uniformly, we bound them in a level by level basis. So it might not be obvious why this is a refinement. Let me make a simple observation that so long as all the gamma j are smaller than 1, they're strictly smaller than 1, the right-hand side is always going to be strictly smaller than 1. So the gamma j are smaller than 1 precisely when all the graphs G alpha are connected. So long as we have this basic connectivity criterion met, the bound we give on the second singular value is always going to be non-trivial. And indeed, this is because of this that we no longer require gamma to be order 1 over d squared. So this opens new avenues for the use of local spectral expansion beyond sampling matroid basis, which was the application of unary UNOA square n in resolving the matroid expansion conjecture. Okay, let me talk about a few applications that have emerged from our work. So one is the application of Lapchi and I from our paper on sampling independent sets of fixed size. There is this folklore result that says whenever you have a graph of maximum degree G, you can just do this down-up walk on the collection of independent sets of size n over 2 delta, and it's going to be rapidly mixing. That is, you can approximately sample an independent set of size k smaller than n over 2 delta. And the proof for this uses coupling arguments, and it's not a hard proof, but it's also not an easy proof. I don't know any spectral proof that does this. What Lapchi and I show is essentially replace this 2 delta with delta plus eta, where eta is the magnitude of the least eigenvalue, sorry, magnitude of the least eigenvalue of the unnormalized adjacency matrix of the graph. And this is known to be between 1 and delta. So it's a refinement of this, in particular when the graph G is far from being bipartite, we get a non-trivial improvement of the folklore result. But what is more interesting is that our result is purely spectral. It uses the theorem I talked about before, and it uses an easy interlacing argument, and it uses Oppenheim's theorem. And by the way, for our results, the bounds we give on the lengths, on the expansion of the lengths, can be as bad as like 1 over dimension. So this is an area where Kaufman Oppenheim theorem can already not say anything. There is another application that have emerged due to the work of Anarli Unave and later Chen, Liu, and Vigoda. This is essentially showing that two spin systems mix rapidly up to the uniqueness threshold. So one example of a two spin system that people care about is the so-called hardcore model, where the goal is to sample from the hardcore distribution for independent sets, where an independent set S is assigned measure proportional to T to the size of the set S, where T is some parameter that is related to the temperature of the system. So White's proved that the hardcore distribution for independent sets has what is called strong spatial mixing. And he gave a deterministic algorithm for estimating the partition functions at D below the uniqueness threshold for bounded degree graphs. So this was a huge breakthrough at the time. Using our results, Honorary Leo and Alice Karam managed to show that this actually works for every graph, in that you can sample from the hardcore distribution for independent sets by using this down-up walk approach, and it mixes in polynomial time, like this random walk. So using the standard reduction between counting and sampling, this actually subsumes White's algorithm for all graphs. Like, this is a randomized algorithm. I'm not sure whether people care about randomized versus non-randomized, but this is interesting. And what is quite new is an extension of this result by Chen, Liu, and Vigoda to all two-spin models. So they show that all two-spin models actually, you can show fast mixing for all two-spin models using these methods. Okay, so let me now say a few words about how we prove our results. So we have this down-up walk that starts from the level xt, goes to the level xt minus 1, and then goes back to level xt. You can think of this as a two-step random walk on a bipartite graph, where on the right-hand side we have d-dimensional faces, and on the left-hand side we have d minus 1 dimensional faces. So if you write the adjacency matrix of this, and if you take the squared, then on the one block, you're going to have the down-up walk, which is corresponding to a two-step random walk starting from the xt side. And on the other block, on the other diagonal block, you're going to have a two-step random walk that starts from the d minus 1 side. Okay, and the standard observation we can make using linear algebra is that those two blocks have the same non-zero spectrum. That is, if you just care about their second eigenvalues or second singular values, they're the same. Okay, so what is this other block? This other block is what is called the so-called up-down walk. That is, it goes up and down. And it's described in a similar way where I first start with a d minus 1 face alpha t, and then I sample a d face beta that contains xt, and I do sample it uniformly random among all such faces. And then I sample some element y in beta, and I set alpha d plus 1 to beta without y. And again, this is a two-step random walk, and the bipartite graph H, where we start from the left-hand side now. And by this argument about these blocks having the same non-zero spectrum, we can say that this down-up walk on the level xt and the up-down walk on the level xt minus 1, they're going to have the same second eigenvalue, or rather the same second singular value. Okay, and this is essentially how we do the induction step. Let me also talk about what the up-down walk on the level x0 corresponds to. Again, like, the definition is a little subtle, but it's essentially going to correspond to a random walk on a lazy random walk on this empty link. Okay, like this empty local graph, where instead of alpha I have the empty set. And I do know what the second eigenvalue of this is. Okay, so here's a streamline of inductive proof of the bond that we prove. So essentially, whenever I have a level k and a level k plus 1, I'm going to say that by this bipartite graph argument before, that the up-down walk on level k and the down-up walk on level k plus 1, they have the same second eigenvalue because they're co-spectral. So all I need to do is arguing that the up-down walk on level k and the down-up walk on level k, their spectrum can be related to each other somehow. So in this picture that you see on the left, all I need to show is how to argue about the diagonals, about the diagonal errors. And to this end, I'm going to be introducing this version of the up-down walk that I'm going to be calling the non-lazy up-down walk. And it's essentially a version of the up-down walk that is conditional on not looping. And this isn't a functional dependency from the normal up-down walk. And you can show that the difference between the up-down walk, the non-lazy up-down walk, and the down-up walk on the same level is not that much. And yeah, this is in the PST order. And I don't want to give a full proof for this, but let me tell what the basic idea of this is. The basic idea is that when you condition two subsequent steps of the non-lazy up-down walk on containing the same set alpha, it is as if this random walk is making a random. It's as if this random walk is making a step on the link G alpha. And similarly, if you look at the down-up walk, and if you condition two subsequent steps of this random walk on containing the set alpha, it is as if these two, it's as if these, the step is actually happening on the clique, on the complete graph, on the same vertex set, on the same vertex set on the same vertex set as the graph G alpha. So we have this basic idea that says, okay, if you have an expander graph that is a graph whose second eigenvalue is small, it is like a sparse version of the complete graph. So they shouldn't differ too much. And what we do is actually exactly that. By noticing that this random walk matrix of like this conditioned random walk matrix on alpha, in the down-up walk case is actually just related to the projector to the top eigenspace of G alpha. So this is something like this difference between the two is something that we can bound relatively easily. And from this observation onwards, the statement just follows by what is known as the Garland method that I don't want to get into, but it's essentially a fancy law of total expectation. Okay, here are some questions that I think it would be nice to answer. So the spectral expansion, the second singular value, it quantifies the contraction in the L2 norm, and the modified log-Sobolev inequality quantifies contraction in relative entropy. Can we get modified log-Sobolev inequalities for higher order random walks? So this was recently done for matroid complexes by Krayan, Guo, and Musa. It would be nice to do it for arbitrary Simplicial complexes, arbitrary high-dimensional expanders. Another interesting question, I think, is what are different types of random walks that we can use local spectral information to analyze? So what about the metropolis rule? So what if we allow some, small non-local operations in these random walks? Can we say anything? And another interesting question is whether we can relax the need to have expansion on all links. Maybe we'll look at the average expansion in a local neighborhood. Like, can we use this? So this is certainly not necessary. Like, it's certainly not necessary to be connected in all links. Yeah, it's certainly not necessary to be connected in all links for the random walk to be ergodic. So it would be nice to have a way to, quantify this a little better. Okay, this was all. Thanks a lot.